Hi everyone. Welcome to our 17th session of the MedAI group exchange sessions. This week we have Mayee from the CS department at Stanford here with us to talk about her research on model evaluation under distribution shifts. Mayee is currently a CS PhD candidate at Stanford, advised by Chris Ray. And her current research interests include how to evaluate sources of supervision, such as weakly supervised, semi-supervised, and self-supervised platforms throughout the ML pipeline, particularly through information theoretic and geometric lenses. So thanks so much, Mayee, for joining us today. And before we start, do you have any preferences on how you would like to take questions? Would you prefer us interrupting you, or would you like to take it all at the end?
Yeah, you can feel free to just interrupt me whenever and I can answer.
Awesome. Okay. So as always, let's try to make this session as interactive as possible. And without further ado, let me hand it over to Mayee.
Yeah. Hi everyone. My name is Mayee, and today I'll be talking about some of our work on correcting distribution shift, and in particular with respect to model evaluation. So for an outline of what I'll be talking about, I'll first present this high-level framework about the ML model development process. You've heard it called different things like the model lifecycle or something like that. And this lays out what the key steps and challenges in model evaluation are. Then I'll talk about our main work, which is Mandoline, our ICML paper. And this focuses on how to evaluate model performance under distribution shift. And finally, I'll touch upon some connections to the work of my collaborators that are also focused on other relevant questions in model evaluation. So the standard recipe in building machine learning models is you have some data, you train a model on it, and then you validate the performance, using like your training and validation set split. And so in recent years, we've seen a lot of improvement in how to build models more easily. So focusing on a way that's convenient for people of different backgrounds. There's lots of tools for visualizing how your model is training. There's libraries of various pre-trained models like Hugging Face or NLP, things like that. But there's in general relatively less work in hammering out the frameworks, tools, and methods for the development process in model evaluation. And here I've also kind of circled out this like data circle, because when we think about evaluation, we can't really consider it without the role of data, because a lot of the complexities, the structures, and how your data is given to you motivates what questions you want to study in evaluation. In particular for the data, we can have non-IID settings. So the data is like shifting over time. It can be, pairs can be highly correlated. You can get them from different populations. We can also have that we might not have full confidence on the labels. So our data might be just like weakly labeled or have like some noisy labels. So that makes evaluation a lot more difficult, because when you're comparing your model output and the data, you might not know if your data is right or not. And even in general, sometimes you might have like a labeling budget and you can label a few points. So a lot of times you'll have like a smaller labeled set and a much larger unlabeled set. So how do we really put those together in model evaluation? So these different scenarios make model evaluation a lot less straightforward than just like what we think of when we think of validating a model on like a set of data. And in particular for evaluation, we can think of this in 3 steps, which are measuring, monitoring, and maintaining. And I'll talk about these very soon. But before that, what's playing a growing role that I'd like to draw attention to in this model lifecycle is the role of this side information. And so, because we can't consider this development process, in a vacuum. A lot of times when practitioners are building model, they have some sort of side knowledge or like domain knowledge. And the question here is, how can we incorporate this into these various stages of the machine learning pipeline? And one thing that's challenging is a lot of times this side information can be very abstract or high level. It might be structured in some form that isn't just, nice labeled data points. So the main problems or the main steps in model evaluation, like I mentioned before, are measuring, monitoring, and maintaining. So when we're measuring performance of a model in a data set, we usually think like we're given a data set and we compute some summary statistic on it. We compute like the F1 score, precision or recall, accuracy, and this is just an average over the entire population. But this, we can often miss out on understanding the complete picture if we're just doing that. For instance, there might be some critical subpopulations of the data where we really need the model to perform very well on. Maybe we measure this data set, but we also want our model to be robust to slight perturbations on this data set. So we need to think about beyond just like what this data is that we want to measure. The next step is monitoring. So previously in measuring, we're working with a fixed data set, but as models are deployed and we keep on getting new data, this data is often changing as it goes. So we will need to measure quite regularly how the model is doing on this new data. And the reason is because we might need to determine eventually, our data that we're receiving is so different from the data we've trained on that we'll need to update our model in some way, or the model performance is insufficient. And that leads us to the last point, which is model maintenance. So this question is, what do we exactly do once we've identified a problem? So once we've identified our model performs poorly on a subpopulation, or we've identified, okay, the new data that we're being deployed on is different from the training data. What can we exactly do? Like, do we retrain? How do we retrain? And more broadly, we can ask, what do we do when we just receive some new form of information about the model or the data? And then one final thing to know about this setting is that model evaluation is a continuous process. So we can't just consider it as a one-time thing. And thus we'll need efficient methods in all three of these areas. So we need quick procedures you can repeat again and again as time goes on. So for the majority of this talk, we'll focus on work done in the monitoring steps, so identifying distribution shift and correcting it, which brings us to the paper that me and my collaborators wrote for ICML this year. So along with Karan and Nimit from my lab, and with collaboration with Faye, Kayvon, and my advisor, Chris. So I'll go a bit more into technical detail about what this work is. So as we know, or as I've mentioned, models are often deployed in settings that are very different from those they were trained and validated in. And this can be due to just being how data changes over time. Maybe the training data has some selection bias or something else like this. And to illustrate this concretely, we suppose that our labeled data comes from a source distribution, P of S. And we use this labeled training data to learn a model, F. And then using the label validation set, we evaluate this model under a loss function L or some other metric. And so now suppose we have a different target data distribution, P of T, which is unlabeled, and the model is going to be deployed on this data. So the big question in model evaluation is if we can efficiently and accurately evaluate how our trained model will perform on an unlabeled data set coming from this new distribution. And by efficient, I mean we can't do things like label the entire data set each time we get new data or things like that. So we tackle this question with Mandoline, which is an importance weighting framework centered on how to harness domain knowledge and side information in correcting this distribution shift. And to situate this in respect to the model development process I was talking about earlier, we would want to use this sort of importance weighting framework to decide, to see how our model is performing on unlabeled data. And hopefully this will influence our decision if we need to retrain, if we need to change our model, and kind of construct this workflow.
Can I ask a quick question, Mayee, before
yes.
you move? If you go back to the previous slide,
Mhm.
do you assume that you have access to the entire target data at once, or do you assume like a streaming fashion where you get like parts of the target data which can continuously evolve?
We are assuming that we get an entire target data distribution. So, or just like a large enough batch that we can compute stuff on it. Yeah. But the streaming setting would be pretty interesting, like a more gradual like distribution
Mm-hmm.
drift. That would be an interesting question. Yeah.
Thank you.
Mhm. So, yeah, so when we're correcting for distribution shift, a very common approach is just importance weighting. So in these graphs here are the source and the source and target distributions. And in importance weighting, what we would do is we would just adjust the loss at each point in the original source distribution on the left by the estimated density ratio of P of T over P of S, and this is shown by the blue arrows here. And in expectation, the weighted loss on the source distribution will be equal to the model's loss on the target distribution on the right. But however, there are a few problems with importance weighting. So first is this idea of support shift, which basically occurs when the target data contains samples that have never been seen before in the source data. So these samples will have probability 0 in the source distribution. So when we're trying to upweight something with probability 0, upweighting will not be able to correct for distribution shift on these points. And basically this equation here will just not hold when the supports of the source and target are different. The second challenge in importance weighting is that computing this density ratio can be pretty challenging, especially for high dimensional, very continuous distributions. And in fact, the estimation error for the density ratio can scale in terms of this like d dimension value. So we'll end up proposing a framework that's very similar in spirit to importance weighting, but to see why it might circumnavigate the challenges I mentioned before, let's look at a very simple toy example. So let's suppose we have two features, x1 and x2. So I have like our x and y pairs. And let's suppose the source distribution is proportional to a normal distribution on x1 here, times an indicator variable if x2 is within this range of 0 to 1. And now let's look at a target distribution that looks similar. So again, we have a different normal distribution on x1, and again, an indicator variable on x2 being between -1 and 0. For the model, we can suppose that our trained model doesn't actually utilize x2, so it's only a function of x1. And furthermore, x2 is independent of the ground truth label y in both distributions. So this is a pretty silly distribution shift problem, but we can note that there's clearly support shift on x2. So in the source distribution, our distribution is only defined on x2 being from 0 to 1. And in the target distribution, it's only defined on x2 being from -1 to 0. But it seems like, so there's support shift. But the interesting thing is based on a model and the relationship of x2 to y, it seems like maybe x2 isn't even important in this model evaluation. So the idea to take away from this example is that maybe we don't need to consider all the features to reweigh on. Maybe we only need to keep what are known as like important features. So we'll try to define what important is later, but this is just our motivating example. So our solution is, rather than computing a density ratio on the feature space X, we consider a representation of the data through what we call slices. So these are basically groupings or partitions or subpopulations of the data in some meaningful way. And by reweighting based on just a slice representation of the data, our work shows that it's possible to still faithfully evaluate under distribution shift while circumventing some of the common issues of importance weighting on the raw feature space. So as an example of what slices are, we can consider a sentence classification task, like a sentiment analysis task. And so a user can construct 3 slices here representing negation, male pronouns, and strong sentiment, where each of these basically classify a sentence based on the existence of the highlighted keywords here. such as not, he, him, love, and adore. And so then we can apply these slice functions to the source data set. And so each sentence here yields a binary vector representation based on the presence of the keywords. So like here, I loved eating ice cream. This strong sentiment slice is one, and everything else is not activated. So when we can do the same on the target data set to get binary vector representations. And we'll basically look at distribution shift in terms of these discrete representations. And Mandoline will reweight the source accuracy in the left box over here using the slices to output an estimate of accuracy on the target data. So critically, how well Mandoline works, of course, depends on what properties these slices have. And in the toy example I'm suggesting, we'll want these slices to be important and like not irrelevant, basically. And so we can show that if these slices capture all axes along which distribution shift relevant to the task occurs, then importance weighting with slices will yield a good estimate of the model performance on the target distribution. So notably what this means is that components of the feature space that are irrelevant to the task, which means that they're independent of Y, do not play a role in the reweighting. So the construction of slice-based reweighting can basically ignore these irrelevant features, meaning that we can correct for support shift that happens to occur on those features. Furthermore, we can reduce the dimensionality of the problem from being in terms of the feature space's dimension D to the number of slices K, which is something we can control. And this way we are addressing the two major challenges in standard importance weighting. And here, in a sense, what I've been describing this as is we're taking our source and target distribution and kind of projecting them down to a shared low dimensional binary representation. And so under some conditions that I'll go over, this binary representation will allow us to faithfully evaluate under distribution shift. So here I'm gonna just like formalize what exactly I mean in proposition 1 by relevant and shifting. So this might be a little bit some math if you're interested. And so the main idea is that we can find a representation of our covariates X that can be grouped into 4 categories. So G, H, A, and B of X. And these 4 categories basically depend on if an aspect of the feature vector is relevant or irrelevant to the learning task, and if it's shifting or not, as shown by this diagram over here. So I'm kind of splitting it up into like 2 by 2 categorization. So
quick question.
yes.
Are
Mhm.
G, H, A, and B like probabilities, or are they just binary vector? Like, is it just a 0 or 1?
They're not necessarily binary vectors. We're saying it can possibly be like some other high dimensional vector, but it's just G is binary, but yeah, they're just functions of X. So we can maybe think of it like um, when we look at this vector concatenated, this can maybe be an image embedding of X, or like a word embedding or something that just represents X.
I see.
That like captures everything about it.
I see. Okay.
Yeah. So then, so first of all, we can talk about this B of X. And so B of X is the portion of the covariates that don't change between the distributions. So for the sentence example, we can suppose that all of them have good grammar. So the grammar property of our data points is not shifting between distributions. And for technicality's sake, we basically define that the distribution shift only occurs along things that are not B of X. Next is the category A of X, and this is defined as being irrelevant to the task in the model. So in our sentence classification example, perhaps some sentences have a period at the end, some don't, but let's just say this doesn't really matter for sentiment analysis, even if the proportion of sentences with periods are changing between the source and target distribution. And so the formal definition of irrelevance is with these independence properties. So you can see like A is independent of Y, and changing the value of A doesn't impact the loss function. And lastly, we have G and H. And so I've made this distinction here between G and H, but both of them are the components of the feature space that are relevant and shifting. So the distinction between G and H is that G are the slices that we've identified and we've been able to write as these like simple binary vectors. And H is representing some like hidden component that was not modeled, is potentially too complex to be captured by this binary representation. But assuming that we've identified all of the relevant shifting slices, which means that H of X is empty, we can show that these assumptions allow us to prove that we can do importance weighting using P of T over P of S in terms of the G of X, the slices. So what I have here is just a formal presentation of proposition 1 from earlier. So we'll have this, this new density ratio in terms of G of X. So now that we've determined that we only need to reweight based on the density ratio of G of X, we just need to compute this. So algorithmically, any classical density ratio estimation method can be used on the slices. And in our work, we use what's known as the CLEAP procedure. This is a pretty well-known procedure, but the main idea here is to construct a distribution p hat, which is equal to some parameterized weight function, this W of delta, times our source distribution. And we're going to minimize the KL divergence between this p hat and the target distribution. And we, in minimizing that, we learn our parameterization of this weight, which is equal to this density ratio. In general, this actually gives way to a really nice form when we model our source and target as belonging to the exponential family of distributions, which is a pretty broad assumption, I would say. And we have these various theoretical results on this algorithm in our paper. So for the experimental results, I'll kind of discuss our findings from 2 tasks. So we looked at image classification on the celeb-A dataset, and we look at natural language inference on the SNLI and MNLI datasets. So on celeb-A, we're looking at classifying gender, and we consider distribution shift in the proportion of blurry images. So we can see the source distribution has very few blurry images, while the target distribution has a lot more blurry images, a lot fewer clear images. And we're also constructing slices here based on the metadata itself about the image being blurry or not, which is available to us in the celeb-A dataset. So in this experiment, we're just kind of inducing a distribution shift ourselves and using direct knowledge of the shift to correct it. And this is in comparison to the case where potentially we are not aware of the distribution shifting in terms of the blurry images. And without that sort of information, we might try to work with fitting a density ratio on the raw images or some image embedding, which might be a lot more complex. In the second task, we're considering natural language inference, in particular entailment on pairs of sentences. So I kind of listed some of these sentences just as an example. And the task is that our input X is going to be a sentence and a hypothesis. And the label is if this hypothesis can be drawn from the sentence or not. So on the left-hand side here, we can see a black race car starts up, does not imply that a man is driving down a lonely road. On the other hand, a soccer game with multiple males playing does suggest some men are playing a sport. So this is basically the task. And on the left-hand side here is the SNLI dataset, which is a single genre dataset, which means it's these sentences were generated from looking at images. And on the right-hand side is MNOI, which is multi-genre, which means that not only were these sentences generated from images, but also things like telephone conversations, government texts. So you can see like this is a telephone example. And so the diversity of sentence pairs in MNLI is much higher. So we can assume maybe if we train a model on SNLI and apply it to MNLI, there will be some significant differences. And the slices here are actually constructed in a pretty different way as shown in the bottom here. So what we'll do is actually we'll look at the model score and do this sort of thresholding to construct several slices based on these buckets. And so in a way, we're actually making distinction among the data points on which the model does good or bad on. Because we can imagine maybe the model does well or model does above 0.8 or whatever in the SNOI data set a lot more than the MNOI data set. So here we're kind of targeting differences based on model performance with hope that that's kind of capturing the subtlety of the single genre to multi-genre change. And now here are our results. So Celeb A is on the bottom left and the NOI tasks are on the bottom right. So we can see that Mandoline using these slices is able to correct for distribution shift better than importance weighting on the features themselves. And here the baselines, CBIW, KMM, and UOSIF are other density ratio estimation procedures, and these are done on the raw input space. Our paper also includes further results verifying that Mandoline is a lot more efficient than these other baselines due to lower dimensionality. And we do also compare our choice of using CLEAP in the on the slices against these other approaches on the slices. And we find that in all cases, CLEAP is competitive against other density ratio methods. So to summarize.
Oh, yes. Sorry. I had a quick question in the previous slide. How do we actually interpret the values in the tables? Like, so the source, when you say it's 1.96% and then 1.74%, what does that actually mean? Is that
Yeah, so I guess we didn't include the true target distribution goal, but so the source, this is the error of our model on the source data set. And these percentages are how far, is a little bit meta, but how the error of the importance weighted estimation compared to the target, the true target data's estimation. So I don't have the target average estimation error isn't in this table, but
I see.
Yeah, we would say like we want Mandoline to capture that our model is performing, our model error is like 1.96% on the source, and actually maybe let's say like 3.5% on the target. And so Mandoline comes within 0.16% of that gap.
I see.
Yeah, it's a little bit confusing because these source and the rest of the rows are a little bit different. Yeah.
Makes sense. Okay.
And so, so to summarize, we presented this framework called Mandoline, in which reweighting based on relevant and shifting user-specified slices can allow for efficient model evaluation while bypassing classical problems in importance weighting. And in short, we can see this as a simple framework for quickly checking how your model does on a new unlabeled data set, given that you know roughly how the data is changing. And then, so once we have this kind of monitoring step down in this pipeline, we can kind of use this model evaluation to decide how to update and maintain your model. And so now we're going to actually return to this notion of the full model development process. And this leads us to the final section of the talk. So here I want to take a step back and revisit the other problems in model evaluation and kind of situate them with respect to this work. So one question you might be asking is, does Mandoline rely on slice quality? And the answer is yes, it very heavily depends on the quality of the slices to capture the distribution shift. And while this may sound like a pretty restrictive requirement, we're actually pretty excited about this because we see this more of as a paradigm shift in evaluation that motivates us to think about how practitioners can organize, gather, and iterate on these subgroups of meaningful information. So in particular, we want to ask, how do we produce good quality slices, and where can we get these slices from? So in the experiments, we saw that in Celeb A, we were just using those metadata labels on if a picture was blurry or not. So these are just intrinsic properties of the data. Note that these could also very well be user specified. And then for the NOI tasks, we actually did a task agnostic slice where we were just using our trained models predictions. So basically these two approaches suggest that there's actually a lot of ways to get slices, some of which are maybe user like handcrafted by users, some of which are programmatic. And so a potential framework we've been thinking of for this is that maybe we can collect slices from other sources or other components of model evaluation. And then we can kind of prune this collection of slices down to just get those that are relevant in shifting to plug them into Mandoline. And so let's actually revisit this model evaluation pipeline, and I'll explain this diagram in particular. But so first, we find that slices actually naturally arise, whether handcrafted by users or extracted from models in the measurement stage of evaluation. So let's talk about what work is being done in model measurement a bit more. So the main idea behind why we need to measure model performance carefully is, if we don't, then we don't know what to fix. And so we really do need to take our data carefully and dig through and figure out what we want to evaluate on and how do we do this in a principled manner. So some examples of what we want to evaluate that I've touched on a bit before are, critical data subpopulations. These are very important for, AI safety applications. We also might want to measure on particular subgroups based on, bias and fairness in AI, such as gender and race. We'll want to kind of, filter for that and then check our model on individual subpopulations. And we'll also want to consider if our model is robust to these sorts of like perturbations and transformations. So there's a lot of different things we want to evaluate. And so what's nice is that we have both tools and algorithms for kind of setting up these subpopulations. And these subpopulations can essentially all be used as slices downstream in Mandoline. So on the tooling side, my collaborator Karan developed a toolkit called Robustness Gym that basically supports and visualizes a wide variety of evaluation methodologies. So here the user specifies things like subpopulations to evaluate on, what transformations and perturbations to be robust to. And then this gives out this nice sort of report that visualizes performance across all these subgroups. And what's nice about this is that these subpopulations specified in the Robustness Gym framework plug in nicely with Mandoline. And we basically integrated the Mandoline code and the evaluation under distribution shift into this framework, which is available at the above URL. And then on the model side, on the method side, we kind of want to think about how we even identify these subpopulations. So previously on the tooling side, we were saying, okay, the user already knows I want my model to do well on both men and women or something like that. But maybe we don't know what these subpopulations are. And so that leads us to this big problem in ML, which is the problem of hidden stratification, where there are some rare subclasses that the model might perform poorly on, but coarse-grained evaluation might hide this phenomenon. So as an example, in these chest x-rays, we can see that these models can usually distinguish between abnormal and normal scans pretty well, but there's maybe this rare subclass of abnormal scans, which is lung cancer, where we only have like a very small amount of samples. And so the overall accuracy here kind of hides the fact that our model is performing very poorly on this subpopulation. And so the challenge here is how can we find what these subpopulations are without, when we don't have these labels, and how can we fix them? And so the approach that my collaborator Nimit has been working on, was working on last year, is to just do this very simple unsupervised clustering to identify the subclasses. So in short, they take this trained neural networks features and cluster them. And so this clustering actually kind of reconstructs, the categorization above, like the pneumonia versus the lung cancer fairly well. And they go on to do this like robust optimization for like worst case subclasses. But we can also think of these subclasses as highly informative groupings. And so we can kind of use this clustering approach to generate slices as well. So once we get all these slices, we might want to ask, how do we know what slices are good to use in Mandoline? So this kind of next process of taking the slices and then using them in our framework. So here, the interesting technical question that's kind of future work is to identify what the relevant and shifting slices are. So naively, we can kind of look back at the independence assumptions I mentioned. And we can kind of construct these greedy heuristics for selecting subsets that maintain these independence assumptions. But maybe there's something better here, and that's a pretty big area of future work that we're excited about. Moving on to the next stage of this pipeline is monitoring. So another thing to consider is when we receive new unlabeled data, we were kind of just saying, okay, we want to do importance weighting because this allows us to not have to label any of the new data. But in practice, a lot of times we can definitely afford to label a few points and maybe do some sort of active sampling approach, which brings us to the next work I'm going to discuss. So this is a recent ICCV paper that discusses when we have a labeling budget for the target or validation data set, what points should we label to estimate particular metrics like F1 precision, recall accuracy, things like that. And the catch here is that if our data set is very imbalanced, if we're just randomly labeling points and drawing them IID or uniformly, we might never sample something from a rare class. So instead, we'll sample, their approach basically is they sample from a distribution that's tailored to estimate the particular metric, and they kind of interleave this importance sampling procedure with model calibration. So this is potentially another kind of approach to going about monitoring on new data as we receive it. And so a cool question here to consider is there a nice way to combine this sort of importance weighting procedure that doesn't use any labeling with this active sampling approach? And can they actually help each other? Or just like, can we, for instance, if we're uncertain about certain slices, can we label some data to become more confident that these slices are high quality and capturing distribution shift? So there's a lot of interesting questions here. And then the final step, once we've done our careful measurement on our data set and once we've done our monitoring on new data sets, is to figure out what to actively do to the model. So here I've listed some of the decisions we need to make. So we'll need to decide, do we want to update the model with new information? Or maybe we might say that we are not very confident in our model measurement or our monitoring. So maybe we need to gather more slices or just like carve out more subpopulations to evaluate on. Maybe we need more data because one subpopulation has a very few points in it. So there's all these sorts of like different decisions we need to make. And so the question is, how do we make them? So let's summarize when and why we would need to update a model. So maybe from the measurement step, we see that this model does terribly on a small subpopulation. Maybe from the monitoring step, our model performance on new data falls significantly. And now we don't want to use the model. We want to use something better. We want our model to be better on this new data. Or maybe we just suddenly got new information. So like new data, new features. For example, in recommendation systems, maybe we got a new user or new products or something like that, and we want to incorporate this into our model. So there's a ton of methods in machine learning that we can kind of choose from to decide how to next update our model. So for instance, in this, for the subpopulation setting, we can kind of do like DRO to ensure good performance on a bunch of subpopulations. And in the distribution shift setting, we can just take our weighted loss function and just train on that. There's different, a lot of work on like different variants of a importance weighted loss function you can work with there in domain adaptation, and kind of the list goes on. And so there's a lot of options here for what we can do next. But what's missing as far as my knowledge is that there isn't a very simple paradigm for what's the best way to retrain. And maybe is full retraining even necessary? Like, is there some sort of like warm start or some sort of, something clever we can work with in the model, like looking at the geometry of embeddings or something like that. Because full retraining or these sorts of methods aren't very efficient. And so we can't really iterate on retraining because we recall that ideally in model evaluation, we just want to take our model, update it very quickly, and like keep on doing that until we and like kind of see retraining as a separate thing. So yeah, that's kind of a bit of the future work that we're pretty excited about, and that is the end of the talk. So I'll take any questions.
Thanks so much, Mayee. I think that was a great presentation. Does anybody have questions for Mayee?
I do.
Yeah, go ahead, Ramon.
Yeah. So when you were talking about in the slide where you're defining the slices, like the ones that were relevant and the ones that weren't, you mentioned that there was h of x, which was for the ones that you might not have labels for.
Yeah.
So how do you go about defining that vector? Like, how do you know what you don't know in a way?
Yeah, so this model here is kind of like this is like more of like a I guess like a generative model. We don't actually know what h is here. So are you asking in practice how we would tell if h of x is empty or something like that?
Yeah,
Or
like how would you use h of x?
no, so h of x, like algorithmically, we would never use it because it's just like what we don't see. We make this distinction for the theory because we're like G and H actually capture the relevant and shifting procedures. So when we only have G, there's this kind of like TV distance term with H that is like this bias in our distribution shift correction. But in practice, if we want to see what components, if we want to see in practice how big H is, I'm thinking maybe what we can do is like some sort of like, what we can do is like if we condition on our G and H, and we can kind of check that the distribution shift is like the distributions are equal conditional on G, H, and A. So we would kind of check this sort of thing in practice, if that makes sense.
Yeah. Thanks.
Are there other questions for Mayee? I actually had one more question. So let's say you have like a new class that you're seeing in your target distribution. So it's like a new label or a new set has been added. So it's not a hidden set that is present in your training data that hasn't been identified, but it's a completely new set that you're seeing in your test distribution. So how will you incorporate that knowledge into Mandoline?
So when you said new class, like a completely new
Yeah,
label?
So let's say we are like detecting strains of bacteria in a slide, and then turns out like after a certain time period, like the bacteria mutates, and then you have a new strain that is present now. So that's a completely different bacteria from what you have observed in your training set. So how will that like as an example?
So if we have new labels, so like if our goal was to like classify the bacteria type and we have a new label now, then we're kind of working with more of like a label shift problem. So I guess one thing I didn't completely clarify was our this sort of importance weighting is for covariate shift. So we're assuming that like our P of y given x stays constant
I see.
between the distributions. So that would, what I think you're mentioning is more along the lines of label shift.
Exactly, yeah.
Which is actually very interesting. It's a lot harder than covariate shift, especially if you don't have labeled data. So it's, yeah, I think there's been some work. I think like Zach Lipton's group has done a lot on the label shift and things like that.
Got it. Okay. So I guess like the question about noisy labels would also be considered as a label shift problem. And so do you think basically the solution for that is also something that is yet to be done, or can Mandoline handle noisy labels?
Can you go into detail a bit more about what you mean by noisy labels? So like the you have labels on your target data set, but they're potentially noisy.
Let's say your labels are like crowdsourced, like you do not have experts labeling your data, so you have like a bunch of noisy labels. So your training data is also potentially quite noisy, and your target data is also like noisy, or you don't. It's probably unlabeled. So
yeah. For there though, I guess, I mean, when you have noisy labels, so then your model might be just like naturally not good. But for Mandoline, we're kind of just saying we don't really care how the model was trained. So maybe the model, maybe our like XY pairs are actually noisy here. But there's, as long as there's like no covariate shift, this approach can work.
I see.
Mainly because we're considering the model as something fixed and we're just trying to evaluate it.
Gotcha. Okay. Are there any other questions for Mayee? So if there are no more questions, then let's thank Mayee again with a round of virtual applause.
Great, yeah. Thanks for having me.
Yeah, definitely. I think it's a very important problem, especially in like medical AI, because you really want to make sure your model is evaluated well before deploying. And
yeah, for sure.
And we'll be uploading the talk on our YouTube channel as well today. And so if anybody has more questions or follow-up discussions and want to take it up with Mayee, we'll put you in touch with her as well. And yeah, I guess that's it for this week, and hope to see you all again next week.
Thank you.
Thanks,
everyone.
Thank you so much. Thank you.
Thank you.